The idea of this presentation is just to give you a quick recap on the different accounting sheets and a little bit the flow of calculation on which type of inputs are used for which sheet. And also, I hope in the future you will become more experienced and you will start designing your own accounting sheets. So I'll show you some example of different type of accounting sheets that we can create. So this is the scheme I showed at the beginning. We looked before at the creation of land use map and then interception calculation. Today, the soil water balance modeling for the calculation of the fluxes. And now we're going to use these fluxes to create the accounting sheets. These are the 6 accounting sheets we are going to talk about. And we will see in detail all of them. So the first one is the overview. It's called resource base. I think it's very informative. It gives an overview of the main fluxes in the basin, and it's specifically interesting, for example, to look at overexploitation, the manageable water resources, how much is exploitable, how much should be reserved, utilized and utilizable flow. So that should be a bit clear. It also presenting the inflows and outflows on a monthly and yearly scale in the basin, and makes a difference between green ET and blue ET. So something which is more, which is not easy to manage, like green evapotranspiration is something very hard. But if we want to maybe try to minimize our consumption, we can work on the blue, the withdrawals, and decrease the withdrawals or the consumption there. And also it's trying to quantify the storage change and how this can be of essential during dry periods. This is how the sheet looks like. And if you had some discussions with me in the past, you have seen this sheet before. Now, something has changed from the past. So as you notice, maybe there is no component on the top. In the past, we had some sort of recycling part, which we have removed because we have very little information about it. So it was very uncertain, and we decided not to include it anymore in the next version. And also we have made a separation where now landscape ET is also including some blue ET from these land use types. Now, basically, it's giving you a water balance. So this sheet is kind of the final sheet you calculate, and it's taking into account all the water balance computation we have done. So on the left side, you have all the inflows, and on the right side, you have all the outflows. And the balance is then provided by the storage change. On the top, we report on the green evapotranspiration, and then the lower part, the blue water resources. And what's also interesting to see is the storage change, and to monitor this and to have graphs. Now, this is a general type of infographics on overview of water resources, but might not be ideal for all type of situations. So for example, there is one component here on the left that talks about inflows because of desalinization, but maybe you don't have that in your particular river basin. And the same for maybe you do not have outflow. Maybe it's a closed system. Maybe it's so for just to give you an idea, it's not so difficult to modify this layout, this kind of graphics, into something that fits your specifics. So for instance, it keeps the same philosophy behind, the same type of colors and inflows and outflows, but as you can see, it's only displaying the indicators which are relevant for this particular case in Egypt. So this is a small basin where there is basically no rainfall. So you see all the water is basically blue water, and it ends in a lake. It's a terminal lake, and they are very much interested in knowing what's happening in the lake. So on the right side, where you have the explicitly mentioning the ET over the lake and the storage change of the lake. Okay, now this information I will show you where there is basically a template for every sheet, for every accounting sheet, which you can adjust and decide which type of parameter you want to show. Then we have, and this is based on the water balance that I explained before, so I will not go over again. And this is the way it's calculated. So you have a number of inputs, so some can be collected from mostly remote sensing, but some you need from as in situ or local data. So if you want, for example, to estimate the reserved flow, you need to have information on commitments and legal agreements. So when you, if I go back to this one is a sheet for K2. We have a pretty large outflow, but also because I didn't take into account the reserve flow. So environmental needs or, so not all this water could be utilized. So part of it is probably committed already. So if you do not specify this component, you might think that all this could be used for expanding irrigation, but this is not the case. So this is something we should also estimate, which is this part of the diagram. We do not have, so when you have information about pollution, you can use that. So for example, a gray water footprint map or so to estimate the amount which is then polluted and cannot be further utilized. We have all the flow of calculation related to the vertical water balance. So you need a number of inputs, which we have seen yesterday, and then the model generates a number of outputs which are used for sheet 1. And then we need to have information about interbasin transfer and inflows. We have precipitation, green ET and blue ET, which are also created by the vertical water balance model, and the land use map. These are the inputs, and then we can generate sheet 1. Sheet 2, which is dealing with evapotranspiration, and is trying to point the attention on understanding how much water is consumed by who and in which and when. So when, where water is consumed within the basin. It can help to design some ET management principles for our integrated water resources management plans to make a cap on consumptive use and withdrawals. We also want to maybe use it to understand the impact of land use planning, because land use has also a considerable impact on the consumptive use and exploitable water resources. And like we've seen, I think most people noticed that before, is the differentiation between what is beneficial and what is non-beneficial, which I think is very informative. Also, trying to assess the contribution for different sectors in terms of food security, economy, environment, energy, and so on. This is how the sheet look like. I think you're also, most of you, familiar with it. And you have a part on the left, which is giving some details about the different land use types and how much is the ET and the transpiration for every land use component, and is also explaining, so these are macro, categories of land use, and then all these categories are then grouped into macro categories like protected land uses, manageable or already managed land use types. And then on the right side, you have overview for the entire basin. So here you don't differentiate anymore between land use types. So you have the total, for example, transpiration in the basin in that particular year, 2014, and also this beneficial and non-beneficial. component. For every category in the code, so for every land use type, you have a map. You have spatially distributed maps of ET and transpiration and other components. And then is mapping for every land use type is calculating the total of this. So we know that in all the rain-fed crops, you have 0.8 cubic kilometer per year of ET and 0.4 of transpiration. And this with tables gets split into so much percentage is beneficial. So 3.7, okay, this is too large as a number, but an amount goes to beneficial, an amount goes to non-beneficial and then beneficial. And then the beneficial still gets split it further into different sectors. So for rain-fed crops, you will have a benefit for agriculture and benefit for economy. I can upload the default table, or we can look at the of this table. So the unit is here on top is cubic kilometer per year. So it's a volume. We can change the unit is also an option in the code, in the software, to have it, for example, if you want million cubic meter, or if you want your own unit, you can just add a multiplier and then change it. But everything is expressed in terms of volumes. So large volumes might mean big consumption, but also large areas. So for example, you have large consumption in irrigated crops because there is a large area covered by irrigated crops. These are examples of, again, how we can simplify. If certain classes we do not have, maybe we don't want to have the full reporting, but we can tailor-made this to our own situation. And this is an example again from Egypt, how they have developed their own accounting sheets for their particular case. So they have very few land use types. They have a large desert area and so on. And then they do calculation only for these components. And the flow of calculation there, you start from, I think most of these steps we have seen for calculating interception. And then we also need biomass. So we need to download some biomass, for example, mod 17. But nowadays, this data set has some issues, so it's not available for download. So I use data from Probavi. They provide what they call it DMP. Dataset is also comparable to the biomass from MODIS. And then you have to aggregate this monthly because some data sets are maybe every 8 days or 16 days. And then you can compute transpiration based on the biomass. And you have maps of transpiration. This with the interception and the total ET allows you to calculate evaporation. Once you have that, then you can just simply use this information together with your land use map and reclassification of your land use map to attain SHE2. And these are some of the tables we were discussing before. So for instance, for a protected wetland, 100% of the transpiration is beneficial, 100% of the evaporation is beneficial, and 0% of the interception. And a wetland beneficiality provides benefits for the environment and for leisure, but not for agriculture or economy or energy. And similarly for, like in this case, for the modified land uses, so yeah, we have rain-fed crops. Only the transpiration is beneficial. So all the other components, evaporation and interception, are non-beneficial. And the benefit is mostly for agriculture, a little bit for economy. And in some cases you have, I don't know, for oil seeds, depending on the application, could also be for energy production. These tables are in the software and can be modified. So if you want to adjust these percentages to your own policies. So who am I to tell you what is good for you or what is not? I think you should also have a say about what is beneficial or what is non-beneficial in your particular situation. And what is the goal and what is the aim of your land and water management. Then we have sheet number 3, and has the purpose of assessing and presenting agricultural production, so kilograms per hectare, and can be specific for crop type or can be simply providing the gross biomass per hectare produced in a season. And if you then multiply by the area, you can try to assess the food security, so to get the tons per season or per year. For food mostly, and in some cases you can also estimate feed, timber, and fish production. The sheet 3 also shows the crop water productivity or biomass water gross biomass water productivity in kilograms per cubic meter of water. And by highlighting these two components, you can also look at the gap you have between different crop types or different seasons of this crop. Can be a good instrument to help you planning for future rain-fed or irrigated systems by looking at this together with the information in sheet 1, where you have the exploitable and available water, and it can help you to identify possibilities for saving water in agriculture. So ideally, you can use this as a way to find making agricultural management more efficient. This is how the default one looks like, or default. It's again a simplified version. So on the first part, you have the water consumption in agriculture. So it's the same as sheet 2, but specific for crops, and in this case for seasons. So we have Kharif, Rabi, and Zaid. And we look at the rain-fed ET. And then for the irrigated areas, we look at green and blue evapotranspiration, and then the total ET. And in the second part, we present the land productivity as a gross biomass productivity in this case, in kilograms per hectare, and the water productivity. So you will have one value, for example, per season, or if you have information about crops, then you have the different crops in this component. Again, this can be further simplified. You can make alternative. I just wanted to show you alternative versions, but very similar to each other. So in this case, here they specify the different crops. So they have cereals, they have fruits and nuts, and yeah, and it's only basically blue because they have no rainfall in this particular case. The way we estimate this is, so first we need to get the biomass like we did for the transpiration, but in this case we're really interested in the biomass, and we can do some maybe time series analysis of NDVI to identify crop calendars, or we have information about crop statistics and then we can define the start and the end season of every crop. Then we need to aggregate seasonally the ET maps to get the total consumption per season. And then we have the separation of green and blue. The same for biomass, we aggregate monthly, and then we compute the crop yield, or we just keep the biomass per season. Together with the land use, we get the statistics, and we can calculate also with ET and the crop yield, we can estimate the water productivity, and then we compute averages per land uses, and then we come up with sheet 3. We still have sheet 4, which is looking at blue water resources and particular utilized flows. And it's a way to look at water scarcity because you have both demand and supply, and gives an overview of all man-made withdrawals and can help in preparing water allocation plans. Look at water entitlements and monitor withdrawals if it's compliant with what the authority have decided. And also look at what is consumed and what is non-consumed. So how much is the return flow and how important is the role of return flow on downstream water availability. So this is the sheet. So you have an estimation, this we were discussing earlier about withdrawals from surface water from groundwater. So this is something we estimate, and we have total withdrawals, and this is then split by different land use types. So irrigated crops receive so much water, and their theoretical demand was so much. So in this case, it's almost met. So the demand of the irrigated crops is nearly met by the supply. In other cases, this might not be true. So here it's okay. So it looks like in this particular year, there was no significant water stress in the basin. Now, not all the supply was consumed, so only this amount was consumed, and a part is non-consumed, and this non-consumed will go back into our system. So this is a little bit what the sheet 4 is telling us. So what we want to monitor in this sheet is the supply and demand relationship, how they compare to each other, and the consumed and non-consumed water. Because when we want to, the classical irrigation efficiency will have a better ratio between supply and consume. So ideally, you don't want to have losses. So you want to have supply less and consume. So ideally, you could obtain the same crop productivity by supplying this amount, the amount that is actually consumed. But then you will decrease the return flow. Now, if you decrease the return flow, the amount of water in surface water and groundwater will decrease for downstream uses. So this can also be something you want to take into account. Sheet 4 is calculated using these inputs. So you have leaf area index map, porosity, precipitation ET, interception, and land use. And the water balance model is used to calculate supplies. Then we have reference ET to calculate the demand, the theoretical demand, and with some information about surface groundwater equipped irrigation, you can estimate the supply from surface water and from groundwater, and then compute statistics per land use, and you get sheet 4. Then you want to once you have the total supply can come from groundwater or from surface water, and this supply, a part is consumed as ET or in terms of pollution, and a part is non-consumed. And this non-consumed is usually recoverable and then can be sent to the groundwater system or the surface water system. So you will see this information in the script as well. So sometimes you have return flow to groundwater from groundwater withdrawals, or return flow to groundwater from surface water withdrawals. And the same for this part. So this is return flow to surface water because of groundwater withdrawals plus return flow to surface water because of surface water withdrawals. So you have this crossing in the calculation. Then we have sheet 5, which is used to report on surface water conditions and to give an overview of what is happening to surface water resources. It's used also to give an estimation of the river flow in ungauged river basins, and to make a separation between what we call fast and slow runoff. So the slow runoff is usually the base flow or the dry weather flow, and the fast runoff is mainly driven by the rainfall and by heavy storms. And we use this sheet to quantify the surface water availability and how much is the utilizable withdrawals from surface water. Look at the surface water storages. So these type of calculations we do in sheet 5 and we present in the sheet can also be compared with our data on surface water storage. So that's why we were discussing a couple of days ago about how important it would be to have these records of the different reservoirs, because those are the large storages. But in this case, it's also small reservoirs. It's everything combined within the basin or sub-basin. So there's also split between different sub-basins. And if you have environmental flow requirements, you can also report on that month. So this is how it looks like. You have a kind of a legend on this side, and then you have the total for the basin on this side. And then you have different subbasins. And the arrows are automatically generated depending on the connectivity between the different basins. And then you have, these are different land use types, and you have slow and fast runoff. So you see the proportion of the two and how much is the runoff generated in this particular river basin. On the top, you see how much is the inflow. So in this case, for K2, you have large inflow from upstream. And you have the withdrawals and the return flows. So this is surface water withdrawals that are removed from the surface water system. And these are the return flows. So how much water is then coming back to surface water. If you have interbasin transfer, and here you can see the storage change. So this component is telling you how much is the storage change of surface water. And then finally the outflow. And this outflow is then sent back to the second subbasin and contribute to the balance in the second subbasin. The last sheet is sheet number 6 and is looking at groundwater and the role of groundwater in renewable water resources, particularly for the dry season base flow. Is trying to support safe groundwater withdrawal plans. So you want to make sure there is not overexploitation of groundwater, and is also dividing it by sector. So you can also monitor how much is the amount used for irrigation, for example. Still is important to monitor this and to give advice and see whether what is actually happening on the ground. You also want to make sure you want to see how to perhaps use groundwater as a kind of a storage place for water, for becoming more climate resilient, perhaps, as using groundwater, the aquifer as a reservoir, and also for supporting maybe groundwater dependent ecosystems or springs and wells. This is how it looks like. And you have most of these values are estimated with the soil water balance model, and some are maybe some additional calculation about the withdrawals. So you have vertical recharge that comes from the soil water balance model divided per land use. You could have some capillary rise, some natural kind of abstraction. Then you have the withdrawals from irrigation, for example, this indicator here. And then part of this withdrawal might come back. So you will have some return flow to groundwater and also some return flow to groundwater because of surface water abstractions. Then you want to, we have estimation of base flow. This is calculated by the soil water balance model, and we can monitor the storage change. And then have, for example, this every month or every year and check the trends of this.